Whoop. Hello, hello. Apologies, got the camera all skewy. How's it going? Welcome back. Welcome to the second video in my interview series, going through interview skills and techniques. I see we've got one person live. I see we have no people live. I just say that because I know there was someone who was locked in last time we had interview skills. And so if anyone does join live, I can make sure to sort of tailor it to them. If you have any particular questions or queries, feel free to drop them in, either if you're live or in the comments, and we can kind of go through that. But for today, what I was thinking is to, because I think last time I talked about 5 different general types of skill I think are really important for any sort of interview, be it for Oxford or Cambridge, for natural sciences, or for physics, or for engineering. And those 5 were graph sketching, basic syllabus points, deriving equations and making predictions based on those, learning something on the spot and applying it to a new problem, and finally, just those out there questions, which are designed less to get an immediate correct answer and more to sort of start a conversation and get you to think about the different concepts that might be at play in that particular question. So today I wanted to focus just on graph sketching because graph sketching is very, very important whenever you're doing any sort of interview. They ask it a lot. I'm not sure I've heard of an interview where they didn't ask for some sort of graph sketching. I know in my interview, both interviews that I had were graph sketching, and the second interview was entirely based on the graph sketching. And it's a really good way of understanding if you really deeply understand the math that's at play. So you can kind of get lucky solving equations, but you can't get lucky sketching a graph because it's a single question that asks so many different little bits within the question that it's used to get a really good understanding of how your brain works and what your level is. So I'm gonna, first of all, let me get the mirror whiteboard up. Apologies for that. So I'm gonna get the mirror whiteboard up and we're immediately just gonna go through some graph sketching and go through some of the techniques that I advocate for whenever you're applying yourself to a graph sketch. So first things first, let me get rid of my last live solve of the ESATs just to clear up some space, and then I'll start sharing screen. Get rid of it. Okay, so zooming back in, let me start this screen share. Let's get into it. So we're gonna do mirror whiteboard. Let me just check that it's working. Yep, perfect. So warming up the tablet, we've got, great. So reminding you some of the skills that you need in order to do a good graph sketch. So first thing you're gonna be thinking about, let me zoom out just a little bit actually. First thing you're gonna be thinking about are any axis interceptions. You're also going to be thinking about any asymptotes. So asymptotes, obviously with the vertical asymptotes, you can find those for whenever you're dividing by 0. And for any horizontal ones, you can find it by what's happening as x is tending to infinity. Or minus infinity. Another thing you can consider, are there any turning points? Obviously, taking the derivative and setting it to 0 is a really good way of finding these turning points. Another thing is, do you understand what the general shape should be based on the form of the function? So for instance, if you know it's a quintic, you know it's going to be coming from bottom left and going to top right. You know if it's a quartic, it's going to be doing something like that. Do you have any general information about the shape that you expect? Exponential decay, trigonometry, periodicity, things like this. And finally, are there any special points that seem to require further attention? And I've been giving some graph sketching to a bunch of students this week, and I think I've picked some of the ones that I think are most interesting. These are ones that are definitely, I think, harder than something you might be expected to sketch an interview. So I showed you my interview ones. They were sine squared of x, and they were also exponential decay. So those were relatively simple in comparison. But remember, an interview is a lesson, not a test. And so this isn't about whether you can sit down and instantly get it right. This is about whether you can apply these general principles to the problem and see if you can get yourself at least in the right direction, maybe with a prompt or two. I will add a sixth one, actually, that's come up this week. Can you, if the graph is a little more complicated, can you build it up from its individual components? And I'll demonstrate what that means in practice. So you can sketch your component graphs and see how they compile into a single graph later on. So with that in mind, let's start with one that I've been really enjoying, which is y equals sine of e to the x. And if you are doing this yourself, you can come up with any random combination of exponentials, logarithms, trig, and polynomials. Make up your own thing, see if you can sketch it, and then compare it with what you see in something like a Wolfram Alpha or a Desmos to see if you're right. But let's say you got this one. The first thing you might do, looking at this point that I was talking about right here, this component 6, is building out from the component graphs. So you might draw for yourself as a guide, what does sine x look like? And what does e to the x look like? You want to show good form, so you always want to label your axes and label any sort of special points. Calling that y equals e to the x, this is obviously y equals sine x. We kind of know what's going on, but this can just sort of guide us. So this is pi over 2, this is 1, this is minus 1, etc. So let's have a think about what's happening here. We know it is sine of something, which gives us a chance to sort of lay out a sort of broad philosophy when it comes to any graph sketching. If you're stuck, if you're looking at something and you have no clue what it's going to look like, a really good idea is to see if you can pin down any specific information you can find. So anything you know for certain is going to help you pin down some specific points, and then you can connect them with the shape that you think it's going to be. So for instance here, it's sine of something. And we know that sine always varies between +1 and -1. So we can already pin that down. We know it's going to vary between 1 and -1. Okay, that's good. What else do we know? Well, in general, it might be useful for us to differentiate. And using the chain rule, we know that's going to be e to the x cos of e to the x. We might think, okay, what's the y-intercept going to be? The y-intercept is always going to be when x is equal to 0. And when x equals 0, we can see that y is going to be equal to sine of e to the 0. Well, e to the 0 is 1. And then I'm going to think to myself, well, where is 1? So we're assuming this sine is working in radians. So where is 1? Well, this is why I have my component graph at the ready, so I can kind of track to see where that's going to be. Let's compare it to pi over 2. We know pi is equal to roughly 3, so pi over 2 is roughly equal to 1.5. And we know, therefore, that 1 is going to be between 0 and pi over 2. So it's not quite made its way to that first maximum. So it's going to be somewhere around there. We can also then get some more information about that point. Let's pin it down further. When x equals 0, what's the gradient going to be? Well, when x equals 0, the gradient, by plugging x equals 0 into here, you're going to get that it's 1 times cos of 1. And I might sketch the cos graph for useful information there. We know that by the same exact logic, that cos 1 is going to be somewhere between cos of 0 and cos of pi over 2, so therefore it has to be positive. So we know the gradient is going to be positive through that point. We also know that sine is going to have a value of 1 at very specific points. And we might find maybe less that. Let's find the 0 points first. As we found the y-intercept, let's go ahead and find the x-intercepts. So I'll get rid of that just for now. Ooh, apologies. And let's find those x-intercepts. So that is going to be when y is equal to 0. And that will be when sine of e to the x is equal to 0. Now I know from having sketched my component graph, I'm going to get zeros on the sine graph every n pi. And then I can solve for x by taking the natural log of both sides. So n pi, okay. Well, what do I know about n? I know exponential can never be negative. It can also never be 0 from this component graph, which I can refer to. So the smallest value of n I'm going to have is 1. And it's going to be going up from then. So the first 0 is going to be when n equals 1. So the first 0 is going to be when x is equal to ln pi. And that is going to be the first 0. So it's going to go up. It's going to come down. It's going to hit ln of pi. But based on that logic, based on the fact that that has to be the first one, it means that there can be no zeros for smaller values of n. So then I'm thinking, okay, what's happening on the left-hand side of this graph? Let's think about that. Well, first of all, I can see something special. I can see that as x tends to minus infinity, e to the x is going to tend to 0, which means that y is going to tend to 0. And the gradient is also going to tend to 0 because of that at the front. So that immediately tells me there's going to be some sort of asymptotic behavior. And we can understand this because the values on this e to the x graph are the argument that go into the y equals sine graph. So as I look here, as x tends to minus infinity, this argument is going to tend to 0. And as the argument tends to 0, I know I'm going to be approaching exponentially slowly this point here at the origin. You might also qualitatively then say, okay, well, if this is the argument that goes into the sine graph, well, I've tracked it going that way. So what happens if I track it going this way? Well, as I increase x, I will move exponentially quicker through the argument. So I might expect to move faster and faster through the sine graph and have the periodicity get bigger and bigger. So qualitatively, I might sort of expect a general shape to be doing something like this, etc. I can kind of get a sense of that, but I've got an intuition, but now let me see if I can pin this down a little bit further. So what I might do is I might track these other crossing points and see what I can find out. Well, if it is true, well, let's find the other one. So I know the first crossing point is ln pi. The second crossing point is going to be ln of 2 pi. The third crossing point is going to be ln of 3 pi. And what I can do actually is get a general expression for the difference between consecutive crossing points, between consecutive x-intercepts. And if I do that, let's call that xn plus 1 minus x of n. Well, x of n plus 1 is going to be ln of n plus 1 lots of pi. And I'll subtract off from that ln of n pi. Using my log laws, I can combine those into a single log, and the pi's will cancel to give me this, which I can then also break out further to say this. And so as x tends to infinity, we know that n also tends to infinity, which means that this difference in x-intercepts is going to tend to ln of 1, which is 0. So we know that they get closer and closer. The difference between consecutive x-intercepts tends to 0. And we could have got there another way, actually. We could have got there by saying, well, as x tends to infinity, the gradient is going to tend to infinity. In other words, it's going to be approaching, it's going to be less this and more vertical line. And so there's plenty of different ways we can come to an understanding of what's happening in this graph. By writing out the component graphs, you can kind of assemble them based on an intuitive understanding of what happens as I move through this. As long as I ascribe to this its proper meaning, that this is the argument that goes into the sine graph. And anything you think you have the skill to pin down, demonstrate that understanding. What happens to the gradient? What happens to the value of y as x tends to infinity or minus infinity? Maybe I can find this first crossing point, which would have been at ln pi over 2. Sorry, the first maximum point. Anything you can do to demonstrate understanding is a good thing. Second graph I want to go through is, let's do this one. Let's try considering the graph y equals log to base x of 2. So I look at that and I'm like, ugh, I've never seen anything like that before. And so there's several ways of approaching it. The first thing I might do, trying to pin down specific values, pin down specific information, there are certain points I know this is going to have to go through. Because I know that log 2 of 2 is 1. So therefore I know it goes to the point 0.21. I know that log 4 of 2 is a half. So therefore I know it goes to that point. I know that log to base 8 of 2 is equal to a third. So I know it goes to that point. And similarly, I know that log to base a half of 2 is equal to minus 1. So I know it goes through this point. I know that log base a quarter of 2 is equal to minus 2. So I know it goes through this point. No, lies. Hold on a minute. Because a quarter, sorry, that has to be a half. Because it's the minus is going to flip it up to 4, and then the half will square root it down. And so it's just going to be these, but negative. So what I can do at this point is pin down those specific values that I know. I also know that you cannot have a negative base, because a negative number to any power will not give me a positive 2. So it will only exist for x is bigger than 0. And so we also know that if x is equal to, I can get a sense that if x is equal to 1, then 1 to any power will never give me 2, so I shouldn't get a value for x is equal to 1, which implies to me it's probably some sort of asymptote. But I'll hold off on that for a little bit. So let's say I've got 2, 1, 4 half, 8 third, etc. It definitely seems like it's tending towards 0. But I know it goes through half minus 1, quarter minus a half, etc. So it seems to be doing something like that. So I wouldn't be surprised if there's some sort of asymptote at x equals 1. And let me see if I can find some sort of reason why that's happening. Okay, so I've made several claims there based on intuition. Let's see if I can prove them mathematically. Well, what I might do is think about deconstructing this log. So this means that x to the power of y is equal to 2, which I think is clear from all of the points we have them going through. If instead I took the natural log, which I know how to work with and I'm very good at differentiating, I will say that y ln x is equal to ln 2. And so y is equal to ln 2 over ln x. It is clear then that as x tends to infinity, that ln x is going to tend to infinity as well. And because that's the denominator of y, that means that y is going to tend to 0. Okay, so far so good. We also know that ln of 1 is equal to 0, and that would give us a divide 0 error, which means you can then definitely now say that x equals 1 is an asymptote. Just realized I've done bad form. Let's label my axes. Okay, so now we might want to consider special things. So we've got this asymptote down. All right, so we've got this asymptote down at x equals 1. But let's consider the behavior around that asymptote. So let's consider what's happening as we tend to 1 from above and tend to 1 from below. And because I can see a Linux, I'm going to sketch a Linux graph because that's a nice component graph I can understand fully. So I know that y is equal to ln 2 over ln x. And I know that as I tend to 1 from above, then ln x is tending to 0 from above. And we're going to have a positive number divided by a positive number. So the number should always say positive, and it should stretch up to positive infinity. Okay, what else do I know? Well, as x tends to 1 from below, ln of x is tending to 0 and is negative. A positive number divided by a negative number should stay negative. And so it's going to blow up in the negative direction. With this graph, I can also differentiate and find out what's happening with the gradient using, you can either do quotient rule here, or you can use the chain rule, arguing that that is equal to ln 2 into ln x to the minus 1. And that's the form I'm going to use. So if you differentiate that, you're going to find it's minus ln 2 times 1 over x times ln x to the minus 2. In other words, it's minus ln 2 all over x times ln x squared. Now that is interesting for several reasons. First of all, we can look at that and say that is never going to equal 0, because that would imply that ln 2 equals 0, which it is not. So there will be no turning points, which is good because it means this thing never turns around. But this tells me something else that is very interesting. So we can see that the gradient is going to go shooting off to infinity when x is equal to 1, which makes sense because it's the asymptote. But this also tells us that the gradient goes shooting off to infinity when x is equal to 0. So it implies as we tend to 0, it should go vertical. So it's going to do a sort of vertical thing, move through the points, and then go vertical again down to this infinity. But we know that obviously you cannot have 0 itself being a base, because 0 to any power will not give me 2. So it does not actually touch the origin. It doesn't go through that point, but from that point, it's going to shoot down into the negative, then curve through, and then down to this asymptote on this side. And then it's going to go shooting up from infinity down to 0. Another graph we might consider is y equals sine squared x over x squared. So if you watch my first video, you'll see that this is derivative of a question that I got asked in my actual interview. As before, I'm going to sketch out my component graphs. So y equals sine squared x. In fact, let me make sure I do this in the positive x and the negative x. That looked something like this. So let's pretend that this was an extension of that question that I got asked. I know that this is what y equals sine squared x looks like. And I also know what the y equals 1 over x squared curve looks like. This is just basic syllabus. So then I can think about what happens as I multiply them. Well, what's going to happen is first of all, we can get some understanding here. So as x tends to infinity, I know that y is going to tend to 0. And as x tends to minus infinity, y is also going to tend to 0. And what we can see is that the amplitude of the graph, I can also tell that this is always going to be positive. But as x gets bigger, we are multiplying the sine squared curve by a smaller and smaller number. And so the amplitude should get smaller and smaller as I move away from the origin. So I might start by saying, okay, well, if that's going to be true, then it would start there. It would do something like this. And then it would do this. And then it would do this, etc. Okay. So this might be my initial graph. But then I might want to think and I might say, hang on a minute, but there's a special point to consider here. Because actually the amplitude here would be infinity and we'd have a 0 times infinity, which is kind of weird, right? So how do I handle that in an interview situation? And this is why I considered that fifth thing, considering special points. So how would I consider the special point where x is equal to 0? That would be 0 over 0, which I don't really know how to handle. So what I could do maybe is think about what happens around 0 when x is very small. There is a skill I have for my syllabus that I can apply to this question, which is the small angle approximation. If I apply the small angle approximation as x tends to 0, I know that this sine of x will roughly tend towards x. So this will tend towards being x squared over x squared, which is 1. Great. So I actually know it's going to go through the point 0, 1. But then the question becomes, where is that on my axis? Is that going to be here? Is that going to be here? How am I going to handle that? So what I'll do in that situation is I'll find a point of comparison, specifically this. I know the first maximum on a sine squared graph is going to be at x equals pi over 2. And I know that 1 over that, so that's times 4 over pi squared times 1. So that should be the amplitude. So I know the exact coordinates of this point. From here, I can compare pi squared with 4, pi being roughly 3, that's going to be roughly 4/9. That is very much less than 1. So I haven't drawn the axis quite well enough, but so it's going to dip up somewhere up there. So apologies for the fact that it's not completely accurate, but I can see that it's going to do this big curve. So in fact, what I might do at that point in the interview situation, let me just redraw it. Okay. So it's not quite going to do that. So what it might do is it might look something more like this. And then what I might consider are these 0 points. Well, I know that the zeros here are going to be at every pi. And so what you can see is this central maximum, which is very large and twice as wide as all the others. And then an interviewer might look at you and say, does this remind you of anything? And hopefully you would be able to say, yes, this reminds me of the diffraction pattern for single slit diffraction. Central bright fringe, twice as wide as all the other fringes. And you can see then that they might introduce particular graphs that have particular physical significance. We could also maybe differentiate this to find any turning points, just in case they ask it. So what we could do is we can apply quotient rule here and say that dy dx is equal to bottom d top. If I differentiate that, I'm going to be getting 2 sine x cos x minus top d bottom all over bottom squared, which is equal to canceling an x, 2x sine x cos x minus 2 sine squared x all over x cubed. Let's move down and sort of work on that a bit further, because I know I can take a 2 sine x out of that and be left with x cos x minus sine x all over x cubed. So we can immediately see that whenever sine x is 0, the gradient will be 0. So every time you get these zeros here, it will be a turning point. And we also seem to have 0 points. In other words, these maximum points when x cos x minus sine x is equal to 0. Well, that means that x cos x is equal to sine x, which means that x is equal to tan x. Now that gets interesting because I'm not sure I can solve that analytically. And why might that make sense? Let's explore that a little bit deeper. So here, let's compare this with the sine squared curve that we had before, where we knew those maximum points analytically. We knew this was going to be pi over 2. Oh, have I assumed then? Well, no, it definitely goes through that point. It's just that might not be a maximum. So we know it does go through this point, pi over 2, 4 over pi squared. So I do know that this was still good for telling me that this central point was going to be higher than that point there. But I have a feeling this is telling me something interesting. I have a feeling this is telling me that these maximum are not where they used to be. Have I done this right? Hold on a minute. No, that definitely, there should be infinite solutions to this graph. Reason being, so let's find out what's happening here. So if I sketch tan x, I know it's doing this. And I know if I draw, I mean, this is now awful, but whatever, excuse me. If I draw a straight line through that, that's a big if. Can I draw some? All right. I'm sorry. What we can see is it's going to cross at the origin. It's going to cross each branch of this, and with every repeated unit of tan, in fact, I'm not even sure it will cross that twice, but it will definitely cross these every time you get a periodicity. It's going to cross, but that periodicity is not going to be pi. Now the plot thickens. It would be pi if it was that to the exact same spot, but it's not the exact same spot. It's a little bit further down. So that tells me, first of all, that these maxima are not going to be at regular intervals, and they're not going to be exactly where they were before. Because if we plug in this point, where x is equal to pi over 2, into this gradient function, I don't think we're going to get 0. So for instance, okay, let's plug in pi over 2. Well, we're clearly not there. But let's plug in what the next one would have been, which is 3 pi over 2, which is where I might expect it to be. Let's plug that in and see what happens. Well, 3 pi over 2 on sine is going to be minus 1. Yep. So that would be 2 times minus 1 into, well, that would be 3 pi over 2. Cos of 3 pi over 2 is 0, actually, so I can just ignore that. that would be minus, minus sine of x. So it would be 0 plus 1 all over 3 pi over 2 squared. Cubed even. So it'd be a little bit negative. Now, why does this matter? So actually, this place where we thought, and you can see I've followed my rabbit hole fully now. I'm kind of curious. I want to get in. But this is what you do, right? You get curious and you get excited and you show them, ooh, this is something I quite like doing. Let me apply my skills to gain new insights. What that means is this point that should have been a maximum is no longer a maximum. And in fact, the gradient looks to be negative there. Specifically, minus 2 over 27 pi cubed over 8, which you can't see because I'm covering it up. And that would be minus 16 over 27 pi squared, which is not small, but it is decidedly negative, which means that instead of that being a maximum point, it's already decreasing by that point. And why does that make complete sense? Well, what's happening is this point, this curve here, where there would have been a maximum there, we can see the left-hand side of this curve where it was increasing has a larger 1 over x squared value than the values on the other side of the maximum point. And why does that matter? It matters because these then are getting stretched up and these are getting stretched down. So you would expect these points here to be lifted up higher than the old maximum point was. So we get a little bit of this bump where it's a little bit skewed towards the middle, which I find really interesting, that actually. I definitely don't expect you can see I've just now gone all over the place, but that shows what you could do. And in a real situation, they won't let you fully monologue for 40 minutes on a single graph. So what they're going to do is guide you. They can stop a line of reasoning and say, okay, you've shown that you can do that, but for the purposes of this question, let's just consider this point. So you might be thinking long and hard about every time they give you an intervention, really parsing out the individual words they're using, getting the most meaning out of it and playing that mind game. Like, okay, where are you trying to lead me here? What are you trying to get at? So I think I've pretty much exhausted that graph. But that's fascinating. I actually hadn't picked that up before, ever. And the final one I really wanted to go through. Actually, no, there's a couple more. And I've got time. I promised an hour, so I'll give a full hour. Let me consider the graph y equals cos of root x. So as I look at that, I know there are going to be 0 points. I know that when x equals 0, I'm going to get cos of 0, so it's going to start at 1. I can find where that equals 0, so I can take the component graphs. Well, first of all, I know that root x is going to look something like this. And I know that it's only going to be true for positive x, clearly. And I can draw the constituent cos graph for positive x, which is going to look something like this. So pi over 2 pi, 3 pi over 2, 2 pi, cool. So then, let's have a think about what's happening. I know that y equals 0 whenever root x is equal to an odd number of half wavelengths. I can square that up, and it's going to be x is going to be equal to n plus a half squared times pi squared. And I can play the same game that I played before. Let's find the distance between consecutive x-intercepts. Well, the next one would be n plus 3 over 2 squared, pi squared, minus, and just the normal n plus a half squared, pi squared. Let me expand this out. N squared plus 3n plus 9 over 4 lots of pi squared, minus n squared plus n plus a quarter lots of pi squared. So taking out the pi squared, we can see that these are going to cancel. You're going to be left with 2n plus 2. And so we can see that this, therefore, is going to increase as n increases. So I would expect the intersection points to be getting further and further apart. I could also get there qualitatively from this graph by understanding, if I label my axes properly, that this is the y equals cos x graph, and this is the y equals root x graph. And this, if I ascribe this some meaning, the significance of this graph is that that is going to be the argument when I plug it into here. So what's happening to the argument as I move through x? As I increase x, the argument is increasing, but at a slower and slower rate. So the argument is progressing slower and slower and slower. I'm moving slower and slower through this cos graph. So I would expect it to maybe look like a cos graph. So my intuition based on everything I've pinned down so far says that it might do something like this, where it gets wider and wider. But then that raises an interesting point to consider. What happens there? What happens at x equals 0? And to find out the behavior around any point, that's a good idea. So that's a good context clue that you're going to have to differentiate and consider the gradient. Because what is the gradient? It's how the function is changing around that point. So let's differentiate this. So I'll rewrite it just to have some space to work. So y is equal to cos of root pi. Differentiating that, we would get a half x to the minus a half, and cos differentiates to minus sign. So this is using the chain rule. And so that's going to be minus sine root x all over 2 root x. So again, we're going to have a problem when we plug in x equals 0. We're going to have the problem that we get 0 over 0, which just blows up. So what I'm going to do is, like I did before actually, consider what happens as x tends to 0. I'm going to be using my small angle approximation. And when I do that, I know that sine x is approximately x. So it will be approximately equal to minus root x over 2 root x, which cancels down to minus a half. So in fact, this point here is not the same turning point that it used to be. Instead of having a gradient of 0 at the y-axis, it's going to have a gradient of minus a half. So it's going to start off, oh, it's gone now. So it's definitely going to start off with some downward momentum. So it's going to look something like that, where, and let's be a bit more specific. So it's a cos graph, so it's still going between 1 and minus 1. We know it's got that initial downwards behavior, and we know it crosses the x-axis when at every one of these. So when n equals 0, we have pi squared over 4. When n equals 1, we have 9 pi squared over 4. When n equals 2, we have 25 pi squared over 4, etc. So it's all the odd squares over 4 times pi squared, which will clearly get bigger and bigger. So we've nailed that down. And the final graph I want to consider today is one that I just came up with completely randomly that I've been having some fun testing some students with, which is y is equal to e to the 1 over x squared minus 2x minus 3. And this is a really good graph to demonstrate the principle I outlined earlier, which is to build up these component graphs. So I might start from something that's much easier to do, which is that quadratic by itself. So let's consider y equals x squared minus 2x minus 3. I have my skills for my syllabus. I know I can factorize that. I know I can therefore find the 0 points. So these are going to be my x-intercepts. I know that so it's going to cross at minus 1 and 3. I know it's going to cross here at -3 when x equals 0. I know that's going to be at 3. And I know I can complete the square on that to work out the turning point. So that's going to be at 1 minus 4. Great. I know everything I need to know about that graph. What I might do then is do 1 over that graph. So to do 1 over that graph, I'm going to line them up because I know wherever, so if that is x squared minus 2x minus 3, to do 1 over that, I know when I'm this now has a physical significance. This has a meaning, which is it is now the denominator of the other graph. When the denominator is 0, I know I have a vertical asymptote. So here at x equals -1, I can draw my vertical asymptotes. I can then consider what's happening. Well, first of all, I know as x tends to infinity. Well, let's just use this. We'll just use this as the denominator. As x tends to infinity, the denominator gets bigger, 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 and shoots off to infinity. So this will tend towards 0, because 1 over a massive number will tend towards 0. And same thing in the x tending towards minus infinity direction. We can see that this denominator is shooting off to infinity. So 1 over positive infinity is going to be 0. And what's more, positive over positive is positive. So we know it's tending to 0 from above. What else can I say? Well, let's see what happens as we approach that asymptote. So as we approach 3 from above, I know that the denominator is approaching 0, which means it's blowing up to infinity. But more than that, this is positive in this region. So positive over positive is positive, and it's going to blow up towards positive infinity. By the same argument here, the denominator is tending to 0 and is positive, so it's tending towards positive infinity. And I can immediately draw on the shape here. I could probably also have made that argument by arguing that there is a line of symmetry in this denominator about the point 1 minus 4. So I would expect 1 over this graph to have the same line of symmetry. We can then consider this point here. So if we're dividing by something, if we're dividing by the smallest thing, dividing by a minimum, that will yield us a maximum. So we expect there to be a turning point here at the point 1 minus a quarter by plugging that in and flipping that over. So 1 over minus 4 is clearly minus a quarter. And I can also think, what happens as this denominator tends towards 3 from below? Well, sorry, as x tends to 3 from below, the denominator is going to tend to 0 and be negative. So when it tends towards 0, y blows up to infinity. But importantly, it's to minus infinity, because positive over negative is negative. So it's going to do that. And by the same argument, it's going to do the same thing on the other side, crossing here at the point 0, a third, minus a third. Great. So now we know everything we need to know about y equals 1 over x squared minus 2x minus 3. Let's now consider taking the exponential of this graph. Now I'm going to look at this top graph and say that this is going to be my component graph, where what I have to consider is that is the argument of the exponential. I'm not sure if argument's the right word to use there. Maybe power. I'll use the word power. So when e to these powers is what I want to plot. Well, let's consider all of these points that I've pinned down previously. I know that e to the power of 0 is going to give me 1. So as x tends to infinity, I know that y is going to tend towards 1. And by the same logic, as x tends to minus infinity, y is going to tend to 1. So I can draw on that asymptote. Let's say that's going to be the long behavior out here. I also know that e to the power of infinity is also going to be infinity, so it will have these same vertical asymptotes, whereas e tends to positive infinity. As the power tends to positive infinity, so does the exponential of that power, so I'll get these same asymptotic behaviors there. But I know that as the power tends to minus infinity, e to the minus infinity is 0. So here, at these points of 3 and 1, on the left-hand side, where it was minus infinity, on this graph, I should get a value of 0. And same thing here. E to the minus infinity is 0. In fact, let me draw the exponential graph because that's an important component graph. So we can see that as when x is negative, so when the power of the exponential is negative, it is less than 1. And as the power increases towards 0, or as the power increases towards 0, the value I get increases from 0 up to 1. So it will not reach 1, but it will increase up to that maximum and then come back down where the maximum point should be 1 e to the minus a quarter. And I know it's going to cross at 0 e to the minus a third. Now, this was weird because normally you would think things should approach but never reach an asymptote, but this seems to be touching the asymptote. I suppose the argument there is it's only asymptotic behavior on the right-hand side of that graph. But these look like special points I want to consider further. So what I might do is differentiate and see if what the gradient is there. So is the gradient doing anything weird? Is it vertical there? Is it horizontal there? Is it coming off at some sort of angle like I've intuitively drawn it? Let's find out. So I'll differentiate. And if I rewrite that as e of x squared minus 2x minus 3 to the minus 1, by applying the chain rule here, you're going to get minus 2x minus 2, x squared minus 2x minus 3 to the minus 2 from differentiating this guy. Exponential of 1 over x squared minus 2x minus 3. And if I simplify this, well, 2 minus 2x all over x squared minus 2x minus 3 squared, which in fact, let me write that out as the factorized form. So that's going to be x minus 3 x plus 1 squared. And I'll factorize that out as well and call that 2 into 1 minus x. E to the stuff. Now that's interesting because... Oh, don't do that. No! Why? Okay, so this is not what I wanted. And again, this is kind of a live solve for this particular bit because I haven't gotten this deep with any student yet. So bring it. What am I seeing here? I'm seeing as x tends to 3 from below, I know that this part will equal 0. I know that this will equal 0. So I get another 0 over 0 error. Am I going to be able to resolve this? Well, I'm not doing a double L'Hopital's rule on that. Because L'Hopital's wouldn't even work because I could differentiate this as much as I like. I'm not getting anywhere. So can I use small angle approximation? Not really, because it's not close to 1. or sorry, exponential is not close to 0. In fact, the power is very much not close to 0 because it's minus infinity. I know that the skills you need to solve this are not there in the A-level math syllabus, and this is definitely further than an interview would go. What I can say from this with certainty is that there is a turning point here when x is equal to 1. Oh, and another thing I can say with certainty, though, is... Oh, no, I can't. Yeah, I was going to say, okay, when this is 0, which it never is, except for maybe at that point. So I don't know if they're flat or not. That bothers me. Well, so e to the minus infinity, can I solve this? Maybe. Maybe? Maybe? Because then this, I could rewrite it maybe as, if I write 1 over x squared, this might be an idea, it's probably not, but if I rewrite that as just a generic g of x, then dy dx would be 1 minus x times this thing squared times e to the g of x. Does that tell me anything? Well, no, because that thing's blowing up to minus infinity. Which one's going to blow up faster, I wonder? But that would be taking the double different. I'm going to say no. I think I'm satisfied. It definitely bothers me. And I think with further math, there might be a way of doing this, but I haven't taught this part of the further math in a while. If you've indicated you've done the further math on your supplemental questionnaire, maybe they could ask it, but hey-oh, it's a lesson, not a test. And I've definitely shown them what the skill I've got is, and I wouldn't feel bad about needing a hint at this point of saying, do you know what? That's beyond me. I'd be very tempted or very, very keen when I absolutely get in to find out how to solve this analytically. And the real thing, I might ask them a question. I doubt they would guide it to this point. But this, showing that kind of curiosity, I want it. I want to solve the problem. That is the kind of stuff they want to see, that kind of relish for the challenge. And that kind of throwing things at the wall and refusing to give up and coming up with new techniques. So even though in this situation, I'm not coming up with the correct answer, I'm still demonstrating the qualities that they would want to do. So this would count as a positive outcome in an interview, even if I can't get the right answer for exactly what's happening in the behavior around those points. And I think that is probably a good place to stop for today. So going through then, what I think the most important things I demonstrated today were, first of all, drawing your component graphs. If you can see it's made up of different components, drawing those separately just to have them to hand so you can see how they fit together. Ascribing the meaning, like, okay, that's going to be the argument that goes into the sine graph, or that's going to be the power that goes into the exponential graph. That kind of stuff could be very important. Pinning down specific things that you can find out for certain. Intercepts, y-intercept, x-intercept. What happens to infinity, minus infinity? Are there any turning points that you could find? All that kind of stuff. Pin it down, understand what the shape is doing in between, see if you can come up with any qualitative understanding of what you expect the shape to be. Maybe see if you can think of a way to analytically prove your gut intuition, because that's the part they want to see, right? Having intuition is great, but stopping at that point shows a lack of curiosity. Kind of get stuck in and be like, oh, okay, yeah, that's interesting. I wonder if I can prove that, though. That's the kind of thing that makes them think, yeah, we can let this person in. They're going to do just fine. What else? I don't know. I'm satisfied. I said it'd take about an hour. That's been about an hour. I think that's good in terms of graph sketching. I'll be looking at the comments. If you have any particular graphs that you think are really interesting that you'd like me to sketch, feel free to drop them in. I promise I will not look them up beforehand. I will do it as a genuine live solve including if that involves me flat, like falling flat on my face. Absolutely no issue with that. But hopefully, I think that gives an understanding of like the philosophy around graph sketching and why it's so important in an interview setting. So with that, I'll call it a day. Have fun, work hard. I'll see you next time.